Jack Jackson. In this video, we're going to talk a little bit about rational functions and analyzing them using pre-calculus and calculus. So first of all, recall that rational functions are fractional functions where the numerator and denominator are both polynomial functions. So it's the ratio or fraction with two polynomials. They actually include the polynomial functions because the denominator could be 1, and they share many characteristics in common with polynomial functions. However, they often have some things that are not found in polynomial functions. And here's a list of some of their characteristics. So first of all, rational functions have as their domain the set of all real numbers except for inputs which makes the denominator equal to 0. And of course, there will only be a finite number of these. So finite many roots of the denominator correspond to discontinuities of the function. And these discontinuities come in two forms. They're either hole in the graph, removable discontinuity, or a vertical asymptote. No other kind, for example, no jump discontinuities, for example. No isolated points. If one of the factors of the numerator or the denominator, if one factors it down, then one can easily identify the inputs which are not in the domain. They're the ones that make each of the factors in the denominator 0. And after you factor that, identify those points in the denominator, the points that make the denominator 0, and those are the things that are not in the domain. They'll either be the places where we have holes in the graph or vertical asymptotes. Okay, so then what you do is cancel out with the factors in the numerator if possible, and look at the reduced version. If those things that made the denominator 0 before in the original version still make the denominator 0 in the new version, then that's going to be a vertical asymptote. If, however, you get an actual number out of the reduced version when you plug in that x value, then that x and y coordinate pair is the coordinates of the hole in the graph. Between the discontinuities, between these vertical asymptotes and holes in the graph, in other words, where it's defined there, it's going to be continuous and infinitely differentiable. So its shape is somewhat similar to a polynomial function there, except of course it could have these vertical asymptotes. But in between, it's connected, continuous, and even differentiable, so no sharp corners. However, this could be in pieces like that. So if you have a linear factor of the numerator that's not a factor of the denominator, that corresponds to an x-intercept. Any x value that makes that factor 0 will be an x-coordinate for an x-intercept. If it occurs multiple times in the numerator, that will also be a factor of the derivative. So the shape of the graph near the x-intercepts depends on the multiplicity of the root there in a manner very similar to that we studied for polynomial functions. So for example, an even multiplicity root is going to touch and turn around on the x-axis, so it'll be a maximum or a minimum, as well as being a 0, an x-intercept. Also, an odd multiplicity root, if it's multiplicity 1, then it will just go, the graph will just go straight through the axis without being a horizontal tangent line there. But if it's multiplicity 3 or 5 or some odd number bigger than 1, it will go through to the other side of the axis, but it will also have a horizontal tangent line there, and it'll actually be an inflection point as well. Same thing that we found for polynomial functions. And that's when you look at the numerator. The end behavior is the same as the end behavior of the power function formed by the ratio of the leading terms of the numerator and denominator. If the degree of the numerator is larger than the degree of the denominator, then the function approaches positive or negative infinity as x approaches positive or negative infinity. So way out on the right or left sides, it goes on up or on down. The arrow will point either up or down. It goes on forever. No asymptote. However, if the degree of the numerator and denominator are the same, then the function has a non-zero horizontal asymptote, the same one on both the left and right side, and its value, the numerical value, would be the ratio of the leading coefficients. If the degree of the numerator is smaller than the degree of the denominator, then the function always has a horizontal asymptote of the x-axis on both ends. Now, look what happens when we want to take the derivative. The first thing we're probably going to do is do the quotient rule. And so the quotient rule, if you have a polynomial p of x or a polynomial q of x, notice that derivative by the quotient rule is the bottom times the root of the top minus the top times the root of the bottom, or the bottom squared, that should say. Let me fix that here real fast. got that fixed. Okay, and notice that what's going to happen is the degree of the numerator, look what it's going to be. It's going to be, this term has whatever power this has. This will have one less than the power that p had, the biggest power of the degree. So when you multiply those two polynomials, you get a polynomial where you add the two powers. So if this one on the top is n, and this one's m, this would be m times n, well, you'd add them. So it'd be n plus m minus 1. And the same thing's true for this one here. So the degree of the numerator of the derivative is one less than the sum of the degrees of the numerator and denominator that we start with. And of course, the degree on the denominator, at least before you maybe do some canceling, is the degree of the denominator, well, times 2. So it's twice as big a degree. Now, sometimes this will reduce and cancel down, so you get something smaller degree than that. But the most you can get is that. So notice that, so if you have degree, if this is degree m over degree n, then you have at most m, n over m. You got at most m places where you have vertical asymptotes or holes in the graph, both that many discontinuities. If the degree of the numerator is n, you have at most n places where it crosses the x-axis. And you have at most n plus m minus 1 extrema. Okay, so let's look at all this. That's all well and good, but let's look at some examples here. So let's see if we can fully analyze this particular function here. F of x equals x cubed plus x squared minus 8x minus 12 all over 2x squared minus 10x plus 12. So that's an example of a rational function. So I would suggest that you maybe try to analyze this on your own and then come back and check with what I've done here. So if you want to do that, go ahead and press pause now. So one of the things that we might do first is to just put it in our calculator and get some technology going here for us to get a graph. So remember to put parentheses around the numerator and the denominator. And we may have to experiment with the window a little bit. I had to play around with this a little bit till I found a decent window. I ended up going from negative 33 to 33 on x. Probably should have marked it off in something less than, bigger than 1, maybe 5s or something, or 3s or something. And then the vertical axis, I ended up going from negative 13 to 22. Again, I marked it in 1s. I probably should have gone up bigger, 5 or 2 or 5 or 10 or something there. Okay, but anyway, you see this shape here. It looks like it's in 2 pieces. Actually, it's in 3 pieces because there's a hole in the graph you can't really see. And then I just did a table here to see some representative values. And look at that. We just sort of stumbled across a 2 and a 3 there. So that indicates that it looks like x minus 2 and x minus 3 are factors of the denominator. In fact, if we factor out a 2, then we get x squared minus 5x plus 6, and that pretty easily factors. So you look at the denominator, factor the 2 out with distributive property. The remaining quadratic factor factors into 2 linear factors, just using good old anti-FOIL factoring there. And so clearly we do see that if x is 3 or x equals 2, this is undefined. Now one of those we can see the vertical asymptote right here, and the other one is going to be a hole in the graph. It's not so visible here, at least on the graphing calculator view. Alright, now, since one of these is a hole and one's a vertical asymptote, well, if you look a little bit more closely, you see that the vertical asymptote looks like it's at 2, but it looks like at 3 is where the hole is. Well, the only way that can happen is x minus 3 is a factor of the numerator as well. So I put x minus 3 here, and I get my other factor. How can I do that? Well, I divide this polynomial, the numerator, x cubed plus x squared minus 8x minus 12, divide it by x minus 3. One way we can do that is with synthetic division. So here's the 3. You bring down the 1. 3 times 1 is 3. Then you add. 1 plus 3 is 4. 3 times 4 is 12. Negative 8 plus 12 is 4. 3 times 4 is 12. And add and get 0, which of course we knew we were going to get. And the other factor is x squared plus 4x plus 4. Which is what I have here, which is actually just x plus 2 squared. So do our anti-FOIL factoring, or really this is just what we call a trinomial square, which gives you a binomial squared factorization. Now we see that these x minus 3's are the same, so we can cancel those out provided x is not equal to 3. And so we get that this is equal to this version right here, x plus 2 squared over 2 times x minus 2. And so notice if we put that in as our y, say y2, be sure you put parentheses around the whole denominator, so that's x plus 2 parentheses squared divided by parentheses 2, open parentheses, x minus 2, close, close. Then you see that these are identical everywhere except for at 3 and 3 comma 12.5 then is our y-coordinate of our whole. And we can also see that by just doing that evaluation on the calculator here, but we could have done the evaluation without a calculator. Plug in 3 plus 2 is 5, 5 squared is 25, 3 minus 2 is 1 times 2 is 2, so it's 25 halves, or in decimal form 12.5. So we see that there is a hole in the graph at 3 comma 12.5, and there's a vertical asymptote at x equals 2. The domain is all real numbers except for 2 and 3. Now I'm going to graph this in Graphmatica in a little bit. Graphmatica will show the hole at 3 comma 12.5, but your graphing calculator doesn't really show that on the graph, but it does kind of show over here on the table. And in fact, you really see it on the table when you look at the simplified version next to it. The one that has a number for the simplified version but an error for the original, that's a hole in the graph, whereas the one that have numbers for both is the same, and that's an actual point on the graph, and the one that has an error both places is your vertical asymptote. Now notice that the only place that, so when is the top equal to 0, but the bottom is not 0. Of course the top is 0 at x equals 3, so is the bottom. That's going to be our hole in the graph, 3 comma 12.5. But once you looked at the reduced version, the things that make the numerator 0 but not the denominator 0, there's only one, it's x equals negative 2. And because that's a multiplicity 2 factor there, it's also going to be a local maximum or minimum. And sure enough, you can see that kind of right here at negative 2 comma 0 is the maximum. There's also a local minimum over here, which I just did by calc minimum on the calculator. Looks like it's, well, it's close to 6.8 at least. It actually turns out to be exactly 6.8, which we'll see in a minute using some calculus. So let's actually find the derivative. Okay, the derivative is in red, the first derivative. So in blue is the original function, which I can reduce to this. We might as well use the reduced version to find the derivative. We just got to remember to keep writing that condition that x is not equal to 3. So I see the 1/2 here. I'm going to just factor that out front. And then I'm going to use the, we're going to use the quotient rule. So that's the bottom times the derivative of the top. The derivative of the top is 2 times x plus 2 to the first power times the derivative of the x plus 2, which is just 1, minus the top, which is x plus 2 squared, times the derivative of the bottom. The bottom is just x minus 2, so the derivative is 1. Over the bottom squared, that's x minus 2 squared. Notice the 1/2, I used the constant multiple rule and brought it out first. Then I was taking the derivative of this without the 1/2 there. Alright, so there it is. Let's clean it up a bit though. Notice that both of these have an x plus 2 here and here, so I factor that out. This leaves 2 times the x minus 2 minus the other x minus 2, x plus 2, excuse me. Now distribute here, let's distribute the 2 and I get 2x minus 4. Distribute the negative 1, I get negative x minus 2. Combine like terms, that gives us 2x minus x is x, and negative 4 minus 2 is negative 6. Still have our 2, which I'm going to put in the denominator. We still have our x minus 2 squared, which is in the denominator as well. So it would be that, provided x is not equal to 3. Or in other words, if we could put in the x minus 3 over x minus 3, then we don't have to write the restriction of x equal to 3, not equal to 3, but we would get this. I think probably this first one, with the restriction being explicitly stated, is probably a better way. But if you typed it like it looks on this right one, in Graphmatica, of course parentheses around the numerator and around the denominator, then it will show the hole in the correct place. Okay, So notice, as I said before, x equals -2 is a place where the numerator is 0, so the f prime is 0 when x is -2. That turns out to be the x coordinate of this local maximum, which is a y of 0. So -2, 0 is a local maximum. Now, it also turns out when x is 6, the numerator is 0 and the denominator is not. So this is x equals 6 is a minimum of the original function. And we see here at the table that 6, 8 is the point we're looking for there. Or, of course, we could just take this and take the 6 that we found by making this 0, take it and plug it back up in this one up here, in the original one, either the very original one or this factored reduced form. Either way, we plug in 6 and we get 8. How about a second derivative? Again, I'm going to look at it this way. X plus 2 times x minus 6 over 2 times x minus 2 squared. Then I'm going to go ahead and take the 1/2 out front, and I'm going to use FOIL in the top and get x squared minus 6x plus 2x is -4x, and 2 times -6 is -12. So I'm going to get the bottom times the derivative of the top. Well, the derivative of the top is 2x minus 4, minus the top, which is that quadratic polynomial, times the derivative of the bottom, which is 2 times x minus 2 times just 1, over the bottom square. So that's x minus 2 squared, which is x minus 2 to the 2 times 2, or x minus 2 to the 4th. So I'm going to go ahead and put this 1/2, put the 2 down here with the x minus 2 to the 4th. Now, both of these have an x minus 2 right here, and one of these, this one has 2 of them right here. Let's factor that out using the distributive property. What does that leave? It leaves me the other x minus 2 and 2x minus 4. And then this leaves me just a 2, make that a -2 because of this negative times that trinomial. Distribute here, it gives us -2x squared plus 8x plus 24. And here we get x times 2x is 2x squared. -4 times -2 is positive 8. Inner product is -4x. Outer product is also -4x, so that's -8x. Now combine like terms. The 2x squares cancel actually, so do the 8x's. And 8 plus 24 is 32. 32 over 2 cancels down to 16 over x minus 2 cubed. And again, all of this was subject to the condition that x is not 3. If you don't want to write that condition, you could go ahead and stick back in the x minus 3 over x minus 3. And if I type it in this last way in Graphmatica, it will show the whole in the correct place. If I were writing it by hand, I would probably prefer to write this version on the left, however. So this is what we get when we graph it. The blue graph is the original f of x. Okay, and notice it has a vertical asymptote right here of x equals 2, and a whole the graph here when x equals 3 and y is 8. Y is 12.5, excuse me. 6, 8, right here is a minimum, and that's where the derivative, the red one, is equal to 0. And the derivative is equal to 0 over here. That's right at the place where x equals -2, I believe it was. Yes, -2, and that's going to be our local maximum, -2, 0. You can see that the derivative has got a hole in it when x is 3, just because as the original one has a hole in it when x equals 3, and the second derivative has a hole when x equals 3. And they all have vertical asymptotes when x equals 2. Notice that the derivative is positive up here, up till 2, and that means the original function is increasing up till -2, I should meant to say. And then between -2 and the vertical asymptote at +2, the derivative is negative. That means the original function is decreasing. Then this little piece right here, the derivative is still negative, so the original function is decreasing. Even between 2 and between 3, which is where the hole is, and wherever this is, I think it was 6, wasn't it? 6 comma 8, yeah. Between where the hole is at x equals 3 and where the minimum is at x equals 6, the original function is decreasing. And then from there on, the original function is increasing, and you can see the derivative is positive. The second derivative, however, is negative over here to the left of the asymptote, so the original function is concave down. And the second derivative is to the right of the asymptote, except for the one point where it's undefined, is actually, well, it's a negative for a while at least, so that makes the original function decreasing. When the original function reaches its minimum at 6 comma 8, that's when the derivative crosses the x-axis at x equals 6, and then it continues to go on up into the positives, which means the original function is increasing. The second derivative, notice, is all negative down here to the left, so the original function is concave down. The second derivative is all positive over here to the right of the asymptote, so the original function is all concave up, except, of course, one place where it's undefined. Now, notice that the degree of the original function is bigger in the numerator than the denominator, so it's going to go off to infinity or minus infinity on the ends. If you take x cubed over 2x squared, that's 1/2 x. So it's going to behave very close to like 1/2 x. So it's going to go off to infinity on the right side and negative infinity as you go off to the left. And it does it kind of like a line. So this one actually has what we call an oblique asymptote or slant asymptote. Let's see, before I get into that, let me go over this. The range is one of the last things we could pick up here. Notice that these arrows here point down. It goes down forever up to 0, including 0. Then it skips over between 0 and 8 and picks back up at 8, going up to infinity. This part would skip over that point there at 12.5, but it's actually picked up over here somewhere. So it actually has all the y values from 8 all up. Okay, I think we said this. Now, since if you want to see what function it approaches as you go off towards infinity or minus infinity, it always approaches a polynomial function on the ends. And the way you can do that is you take your original function here and divide the denominator into the numerator. Okay? You can actually do it in the reduced version as well if you'd like to do that. So I did the reduced version, I think. So the reduced version has the numerator x plus 2 squared, which is x squared plus 4x plus 4. And the bottom is 2x minus 4. And so that's what I have here is 2x minus 4, and I'm going to divide it into x squared plus 4x plus 4 using long division. X squared divided by 2x is 1/2 x. 1/2 x times 2x is the same thing we had here, x squared. 1/2 x times negative 4x is negative 2x. Then change the signs, which I have here in boxes, and use the change sign to add, which will make sure that these will cancel out. So you have to put the right coefficient, even if it involves fractions, on the coefficient, so that you get this to cancel out completely. Now 4x plus 2x is 6x, and still plus the 4 there. Now we take 6x divided by 2x is 3. 3 times 2x, of course, is 6x. And 3 times negative 4 is negative 12. Change the signs to negative positive when you add the 6x and the minus 6x cancel. Positive 4 plus a positive 12 is a positive 16. So this looks like one way we could write this then is the original function is 1/2 x plus 3 plus 16 over 2x minus 4. As x goes to infinity, the 16 over 2x minus 4 is getting smaller and smaller and smaller, and the graph is getting closer and closer to the graph of 1/2 x plus 3, which is our oblique or slant asymptote. And I graphed that as well, and you can see it there, and you see it as this brown line here. Okay, so that one reviews several things that you might see in rational functions. We got to talk about the first and second derivative. We got to talk about an asymptote, vertical asymptote, a hole in the graph. Talked a little bit about end behavior with a slanted asymptote. We use long division for that. We use a combination, if you noticed, of going back and forth between our graphing calculators, our knowledge of pre-calculus with things like factoring and so forth, and long division, some of those skills. And then we also use calculus by knowing what the derivative is and the second derivative using our shortcut formulas, and then also how we can interpret this.